Welcome to ePadasala lecture series in computer science. In this module, we are going to discuss about one of the most important category of problems called NP-complete problems. The objective of this particular module is to discuss about important complexity class related to P class and NP class. We are also going to discuss about the fundamentals of NP complete problems, and I am also going to give some of the most important NP complete problems in computer science domain, so that we can talk about the proof of these algorithms in the subsequent modules. Fine. What is a P class? P class is nothing but a complexity class. P class is a set of all decision problems which can be solved in polynomial time by deterministic Turing machine. Last module we discussed about these problems briefly. All the algorithms that we have been discussing so far are coming under P class. For example, insertion sort is a P class problem, radix sort is a P class problem. What is the characteristic of this P class? P class are solvable in polynomial time, and we can say in general the running time is order of n power c, where n is the input size and c is a constant. Probably you can recollect in one of the earlier module we discussed how to evaluate the running time of the given algorithm. If the running time is coming as a polynomial, then using the asymptotic analysis we can reduce that to the largest magnitude of the power of the polynomial, and we can express the computational complexity of that. Is it right? Fine. There are certain cases where if the algorithm has got a complexity something like order of n power 100, then it is very difficult to compute. But the logic is that, as I said in the last module, these sort of algorithms are very rare, and very often we encounter in computer science problems whose highest power is not more than 3 or 4. In that case, we can say that these algorithms are very efficient and it takes very little computer resources such as memory and processor. Therefore, we call this algorithm as efficient algorithms. Put into briefly, P class problems are solvable in nature, and these problems can be solved in fixed time. But not all the problems in computer science are coming under P class. There are many problems that can be solved by the computer in polynomial time, and we can call those problems as NP class problems. The formal definition of NP class is that NP class is a class of decision problems which are solvable by the non-deterministic polynomial algorithms. These algorithms take a lot of resources. We discussed in the last module. For example, traveling salesperson problem, as the number of cities becomes very larger, the computational complexity time increases exponentially, and these algorithms will consume lots of resources, and it is very practically difficult to talk about the solution of this problem in reasonable amount of time. Fine. What is a deterministic algorithm? So far, all the algorithm which we discussed are all deterministic in nature. So, that means the computers executes the program in a finite amount of time, and it takes decisions based on the given informations. On the other hand, non-deterministic algorithms produce a sequence of guesses and tries to solve the problem using the set of guesses and verifications. Probably you can recollect in one of the earliest module I talked about Turing machines. The Turing machines is a theoretical machine, and theoretical machines can solve any problem in finite amount of time, means then it is the proof of a deterministic algorithms. On the other hand, if there is a problem which can't be solved by the Turing machine, means then those problems are coming under the non-deterministic category. We are going to discuss about these sort of problems only. The prerequisite for the discussion is the need for decision problems. So, a decision problem is a problem whose output is a single Boolean value, yes or no, and if that is the case, then we are saying that NP is a set of decision problems with the following property. If the answer is yes, then there is a proof that can be verified in polynomial time. Fine. Most of the computer science problems are optimization problems. These problems needs to be converted to the decision problems, and the last module we discussed about informally about conversion of the optimization problem to the decision problems. Say for example, if you have a traveling salesperson problem, if that is the case, the optimization problem would be something like finding the minimum cost tour. The same problem can be expressed as a decision problem, something like, is there any path which is less than or equal to d, where d is some sort of a threshold value. So, any problem can be converted to a decision problem, and as we have seen here, decision problems has got only two outputs, yes or no, and decision problems whose output is going to be yes means the problem is solvable, and the important criteria is that NP means there must be some sort of a polynomial, that is polynomial algorithm that is available to check the output of these algorithms. So, we can say that NP problems are very hard problems to solve. By hard, it is meant that computers lacks resources to solve these problems. So, no polynomial algorithm is known for these sort of problems, and if there is a yes, then verification is possible in polynomial time, and most of the optimization problems that are hard can be converted to the decision problems. So, NP has some set of problems like NP odd and NP complete. Co-NP is the complementary NP, is another set of problem that is available. This is just opposite of the previous thing, where if the output of the algorithm is no, then there is a proof that is available that can be done using the polynomial time. And you have one more problem called NPI or NP intermediate problems that are said to exist between P and NP, and NPI is a problem category that consists of problems like factoring and graph isomorphism. Fine. We will take NP as a central core of discussion in this particular module. We will try to define some of the jargons that are related to that. First, we will take the category of NP hard problems. Fine. What is a hard problem? We can say a problem A is NP hard if there exists a polynomial algorithm for that. It implies that using that particular algorithm, all the problems that are coming under NP category can be solved. In other words, it is equivalent to saying that P is equal to NP. So, in short, we have a problem, we do not know whether the solution exists or not. So far the solutions have not been found, fine. If the solution is available, fine, then suddenly all other problems also what you say can be solved by this particular algorithms. So, this sort of problem says that the problem A is as odd as say another problem B. In other words, these problems are problems that are at least as odd as any other problems. So, these problems are called the NP odd problems. Then you have another category called NP complete problems. What is the difference between NP odd and NP complete? Here complete means it is a complete set of problems where if there exists a solution for a problem x, then this solution will provide solution for all the problems that are coming under that particular category. In other words, the entire set will vanish if any one of the problem is solved. And we can also say that the problems in that complete set are so related that one problem can be reduced to another problem in a polynomial time. So, the difference is very simple. NP complete is a set of problems and these problems are well related to each other. Each problem can be reduced to another problem, and if solution is obtained for one problem, then the entire problem set will vanish. This kind of problems are called what you say NP complete problems. One of the biggest research issue is whether P is equal to NP. In other words, suppose if someone finds the solution for the given problem, then the entire set will vanish. In that case, P becomes equal to NP. On the contrary, as of now we do not have any algorithm for that. So, that means whether P is equal to NP is a suspect. Last module we discussed that this is a $1 million problem. Clay Math Institute given a set of problems which are very difficult problems to solve, and you can see that one of the problem that comes here is P versus NP. That means whether we have to say whether P is equal to NP or whether P is not equal to NP, and the solution of this would fetch $1 million. So, this shows that this proof is a little bit complicated. So, now we will concentrate on NP complete problems because these are suspects. That means we do not know whether we have a solution or whether we can give you a proof that whether these problems do not have solutions in polynomial time. So, we will talk about this set of problems. So, as I said earlier, the prerequisite for this is a decision problem. So, all the problems in computer science domain should be mapped to decision problems, and once we have the decision problem, then we can create a language framework. These are some of the important terminologies we have. Alphabet, since this is the decision problem, so 0 and 1 are the finite set of symbols. So, an alphabet is a finite set of symbols, and by combining all the things we get a finite sequence. We call that as a string, and the set of strings formulate a language, and once we have the language, using that we can encode the problem. And as I said earlier, we will use Turing machines for this to verify whether the language is acceptable or not. So, I was telling you that the need for Turing machine in the last module. So, instead of relying on a particular physical machine, it makes sense to create a virtual machine. So, Turing machine is a virtual machine. So, it has got a infinite amount of tape memory, and we have a magnetic head, and the head will move forward or backwards. So, the logic is if the machine terminates in the state which is acceptable, then we can say that the problem is solvable. Please recollect the Turing and Churchill theory also, which says that all the problems that are solvable are solved by the Turing machines. So, using this particular concept, we can say that if the input string is invalid, that means the string that is obtained from the given problem, if it is invalid, then we are going to reject that. If the string is valid, but the output is no, then again we are going to reject the solutions. On the other hand, if the string is valid and the output is yes, that means we are going to accept that. In other words, the problem is solvable by the Turing machines. So, now we can define the NP completeness in terms of the language. So, we can say now that P class is nothing but language L, where L is accepted by the deterministic Turing machine in polynomial time. And we can also rephrase the formal definition of NP complete, and now we can say that NP is nothing but a language L, and L is accepted by a non-deterministic Turing machine in a polynomial time. So, that means we are creating a virtual machine that is non-deterministic. We assume that non-deterministic machines use non-deterministic algorithms. As I said earlier, non-deterministic algorithm uses a set of guesses, and using the guesses the solution is obtained. So, if there is any such method is there, then we can call that problem as a NP problem. So, formally we can say that fine, given a problem Q can be called as a NP complete problem provided if Q is in NP. So, that means we have to give a proof that it is very difficult to solve this problem, and we have to prove that all other NP problem is polynomially convertible or reducible to problem Q. If this is the case, then we can call Q as the NP complete problem. So, here the most important thing is reduction. So, what is a reduction? Reduction is very simple. So, if I want to say that a problem A is NP complete, then I have to take some other well known NP complete problem, and then I have to reduce that to the given problem A. If I could able to do that, fine, I can say that this problem A is going to be NP complete. In other words, reduction form the basis of NP complete problems. This is the second pillar. The first pillar is, as we said earlier, the algorithm must be checked in the polynomial time, and the second pillar is the reductions. Reduction form the basis of all the things. Then we will construct the non-deterministic algorithm like this. The non-deterministic algorithm consists of two steps. One is called the guessing stage and another is called the verification stage. In the guessing stage, what we are going to do is we are going to generate lots of guesses, and in the verification stage what we are going to do is we are going to verify the generated guess, and we are going to say whether the problem is what you say NP complete problem or not. So, the most crucial fact is verifications. What is the philosophy behind that? The philosophy is very simple. Generation of the solution takes lots of time, but once a solution is generated, it is very easy to verify whether it is right or not. For example, consider the simple problem of primality testing. Suppose let us say I am saying please generate a prime number of length 21. It is very difficult to generate that, and if the number is available, I can check randomly by giving certain value, and I can easily say whether the number is a prime number or not. Suppose if I find one instance or one witness that says that the number is not a prime number, then all the effort to generate that long prime number becomes a waste. In other words, verification is very crucial. Verification algorithm has got two components. One is the input string x and another is the string y that we can call as the certificate. What is a certificate? For example, primality testing means the prime number is one number that is divisible only by itself and 1. So, that is the certificate of the primality testings. Similarly, if you take some other problem like TSP, the certificate is like this: a city should be visited only once. So, we can capture these sort of gist of the idea as the certificate. So, in other words, the verification algorithm has got two things, one is x and another is a certificate, and the verification algorithm takes these two things as an argument, and if the output of the algorithm is 1, that means the verification is carried out. So, once we say that the verification is carried out in a polynomial time algorithm, then suddenly that problem becomes what you say NP complete. So, in other words, the role of verification algorithm is very much crucial in NPC, and it must be observed that all the things should be done in polynomial time. One of the important contribution of Cook, Stephen Cook, is the proof that circuit satisfiability problem is NP complete. So, he formulated this problem in 1971. The problem of circuit satisfiability is something like this: given a Boolean circuit, where the Boolean circuit is said to consist of various Boolean gates like not, or, and. The question is there any set of inputs that can make the circuit output as true? If someone gives an assignment that makes the circuit output as true, then the problem is said to be satisfied. Fine. What are the complications? Suppose let us say if there are only 3 variables are involved, the solution is quite easy, because all we have to do is we have to generate 2 power 3 inputs and we can formally verify the output. If the number of variable become 4, then the total number of inputs become 16. In other words, for every unit increase in the input, the output is actually doubled. So, the logic is if n becomes very large, then suddenly the number of inputs that needs to be checked becomes very large, and it is practically impossible to implement these sort of algorithms. So, one of the proof based on this problem is given by Cook-Levitin's theorem, and Cook-Levitin's theorem proves that circuit satisfiability or SAT is NP complete. So, this is the importance of the Cook's theorem. So, based on this we can define lots of problems like satisfiability problem. So, satisfiability problem here refers to the equations. So, Boolean formula has got lots of literals, class and formula. A literal is a variable and its negation like x1 or not of x1. We can combine lots of literals and we can create a class, and we can combine lots of classes to form a formula. So, the logic of circuit satisfiability can be extended for satisfiability, that is, given a formula of all these variables, can we give any assignment that makes the formula as true. So, this is the formula means find what sort of values I can give to x1, x2, x3 such that this formula becomes true. So, you can see that for this set of assignments the problem is satisfied. So, as I said earlier, for smaller instances the problem solving is quite easy, but if the number of variables becomes large, then it is difficult. So, based on this we can form one more problem called CNF SAT. So, CNF SAT is an extension of that, where we put a additional restriction of conjunctive normal form, where every class has got a variables that are connected by the conjunction and all the classes are connected by the disjunction R. For example, this is two classes, and if we put R between these two, then suddenly this becomes a CNF formula. In 3 SAT we give another extra restriction, that is every class cannot have more than 3 variables. If that is the case, then suddenly this becomes a 3 CNF problems. In short, we can say that these 3 problems are good examples of the NP complete problems. So, the implication of Cook's theorem is that fine, if someone has got a problem A and if they want to prove that that is a NP complete problem, then it can be done by reducing any one of these problems, and if someone could able to reduce that problem to the given problem A, then we can say that the given problem is NP complete. Summary. In summary, we can say that P and NP problems are very important. NP complete problems are problems whose status is unconfirmed, and as I said earlier, NP complete problems are solvable by deterministic algorithm, which involves 2 components, guess state and verification stage, where in guess stage we generate a set of guesses that are verified by the verification stage, and SAT problem is a NP complete problem, and the important contribution of Cook is that using any one of these SAT category, we can give you a proof of whether a problem is a NP complete problem or not. Thank you very much. We will meet in the next module.